What's up, y'all? Welcome back. It's Jeff. In this video, we're going to continue our discussion about how voltage measurements work. And specifically, we're going to get into details about polarity, the idea of assigning a positive or negative sign to voltage values. Recall from our last video, we had built a following circuit. We had one voltage source, 5 volts, connected to a single resistor on a breadboard. We also defined an operational definition of the voltage drop across a circuit element. In order to define this definition, we defined two different components. One, we had to define what tool we were going to use. And then the second thing that we had to do is to define a procedure by which we apply that tool to make the measurement. In this case, in order to define the voltage drop across this resistor, we're going to use a digital multimeter. That is the tool we're going to use, which is the first part of the definition. And the procedure is we're going to attach the negative lead on one side and the positive lead on the other side. We saw that when we did this in the last video, we get 4.96. We have not discussed the fact, formally at least, that 4.96 was positive, and in particular in the procedural definition of voltage drop across an element, we didn't actually determine which side we were going to attach the negative lead and which side we're going to attach the positive lead. Thus, if we would have switched the polarity of this measurement, if we would have just changed the black from the bottom to the top, we get a measurement with a negative, even though the electronics behind this don't change. The measurement changes, but the actual dynamics of what's happening underneath are identical. This can be quite confusing, and so in this video we're going to take a look at what polarity in measurements mean with respect to the original operational definition of that mathematical variable. To do this, we're going to switch over and do an analogy between what's happening in voltages and what's happening in springs. Springs are a little bit more intuitive in the sense that we can physically see and touch the underlying dynamics with a spring mass system. Before we hop over to the spring mass system, let's repeat this idea. When we're working with a voltage drop across an element, we can think about voltages as a change in charge. Literally, when I attach this bottom black lead, negative lead on the bottom, and the red lead on the top, and then this says, oh, we've got like 4.96 volts across that. What that means is on the bottom of this, there's a bunch of negative charges, and on the top, there's a bunch of positive charges. And specifically, those charges lead to the ability to move items. In this case, we call the movement, in modern day electrons, we call that the movement of current. If we went back to the origins of this idea, it's physical movement of electrons. So there's this like invisible force field that's passing electrons along that wire. And then the resistor itself is doing something to electrons. So remember, the whole idea when we're measuring voltage across is how much potential is there, how much kind of trapped force, you might call it, is there across that particular element. This becomes really useful in the spring mass system because when we move a spring, there's kind of a trapped force within the spring that can be used to move objects. So remember, when we're measuring voltages, we're measuring the ability to do electronic work, the ability to move electrons. An invisible electric force field passes electrons or passes currents through that particular element. Let's go ahead and take a look at what that would look like in a spring mass system, and then we'll talk about polarity and bring it back to voltages. All right, here we are. We're looking at a spring. And we're thinking about the change in voltage, the drop in voltage across an element, as the same idea as forces in a spring. In order to define the equivalent mathematical variable as voltage drop across an element, let's describe an experiment with respect to springs that gives rise to other mathematical variable or analogous variable, so to speak. So we start this experiment by hanging a spring. We measure the length of that spring with nothing attached, and we call that the equilibrium position because it's at equilibrium. There's no extra force on that thing. And then we fix one end of the spring. So we call that the fixed end of the spring. For the other end of the spring, we call that the movable end. We allow that thing to move back and forth. From there, we apply a force. So we apply a force on the movable end. And as we apply that force, what ends up happening is the spring extends. In other words, as we change the potential on one end, you could think about this as changing the location of that end, there becomes a force stored within that spring. What ends up happening is that force pulls back in the other direction, and we can actually measure the difference in change as a proxy measurement, as a way to kind of get some intuition about the amount of force stored. That's called Hooke's law. So the first thing we do is we mark the position of the end of the spring at equilibrium. Then we mark the position of the movable end of the spring after the force has been applied. And then we call the difference between those the displacement. Another way to think about displacement in normal terms would be like how much length changes. When I start the spring with no mass, pull the thing, look at it at the end of it, what's the change in length of that spring? We see in a different set of labs that the force stored in the spring is a constant times the displacement. That's Hooke's law. The constant is usually called K. Not so worried about that right now. The whole idea, though, is that when we mark the change in length, that talks about some potential to do work, some difference in force on equilibrium versus the end. Let's go ahead and look at what this looks like in terms of the actual experiment. What we do in the experiment is we hang a spring from the ceiling. We allow that spring to kind of get to rest with no mass. We mark the start position, and we'll call that first variable x sub 1. So x sub 1 is the position of the movable end of the spring with no mass on it. Next thing we do is we hang a actual mass, we let it come to rest, and we mark the end position, and we call that end position x2. The difference between that we're going to call the displacement. So the displacement is the end position minus the start position, and in mathematical variables that we say that the displacement associated with that mass is x2 minus x1. With this, we've defined the idea of displacement as the change in position of a movable end of the spring. Let's go ahead and define the operational definition of this. Remember, to do so, we need to define both the tool we're going to use to measure displacement as well as the procedure we use to collect that measurement. In this situation, we're going to see that the tool we're going to use is called a ruler. So we place a ruler next to a situation. In this one, we're going to take 4 different position measurements. The first position measurement is going to be associated with just hanging the spring. The second position measurement is if I put 0.5 kilograms. The third one I put 1 kilogram. The fourth one I put 1.5 kilogram. And then I use my ruler to literally just mark the position of those individual ends of the spring under each scenario along that ruler. Now, the procedure that happens by, I need to choose the location of where I'm going to put the 0 of the ruler, and then the location of where the ruler goes upwards in values. Once I do that, I have this idea that I can then define displacement as the number of tick marks in between those. So in terms of the operational definition, we're going to say the displacement is measured using a ruler, and then we count the tick marks between the 2 ends along that ruler. Let's take a look at what we call the positive polarity. If I set up my ruler in such a way that the 0 mark, the ground of the ruler, is above and the positive position measurements go downward. In other words, we think about the 0 mark as the negative end and the upward counting position measurements as a positive end. The reference direction for this ruler goes from negative to positive in the downward direction. Notice that has a very, very specific impact on the way we actually measure displacement. And when we do this calculation, we see that we get positive displacements in the downward direction. And the reason we got positive displacements in the downward direction is because the reference direction for our ruler, the way that we set up the ruler in this situation, was negative on top, positive on the bottom, and that meant the number of tick marks in here we could interpret as positive. On the flip side, if I switch the polarity of my measurement, instead of putting the negative on top and the positive on the bottom so that positive positions go in the downward directions, I could actually switch the polarity of my measuring tool, in particular, I could put the negative end of the measuring tool on the bottom, the positive end on the top. It doesn't change anything having to do with the actual dynamics, the actual physics, what's happening with my experiment. All that occurs is that when I do this, the measurements that I get are actually the opposite polarity. So in the first case, look, I want to know how many tick marks are in between the initial position and when I put my first mass. Well, check this out. There is a negative 0.4 tick marks because the polarity of my measurement is opposite. Notice that's exactly what we would expect from the standpoint of magnitude, but the signs have swapped. The reason the sign swapped is because the reference direction of my underlying tool, how I assign positives and negatives, are exactly opposite in this scenario. The same thing is said here. Notice that the sign of that measurement is the exact opposite of the opposite polarity because we've switched where the negative and the positive goes. This is directly analogous to what we see when we measure voltages. In the case that we attach the negative end of my multimeter, the negative lead, to the bottom of the resistor where the negative lead of the voltage source is, the positive end on top, notice that measurement is a positive 4.97 volts. In other words, my polarity in this case matches the polarity of my voltage source. When I switch the polarity of my measurement tool, when I swap the negative lead, the negative end from the bottom to the top, it ends up that I get a negative value there because I've literally switched the way in which switched from negative to positive, the way in which I measure that variable. I have a lot more to say about when the actual value of a measurement is negative in terms of the underlying voltage values that we're observing. We will push that off to a later video. But for now, the whole concept of polarity, I think, is quite useful. Remember, the idea is we're going to use a measurement tool to capture data, to capture mathematical variables. The one that we care most about for circuits is the voltage drop across an element. We use a digital multimeter to capture that voltage. When we do so, we have a negative end of that multimeter and a positive end, and the corresponding value of that variable encodes not only a magnitude, but also a sign. And that sign is directly related to the polarity of our measurement tool, where we put the negative and where we put the positive. In the back of your mind, I'm going to coach you. Think about springs. When I use a ruler and it's pointing downwards, I'm going to get the opposite orientation as if I flop that ruler around. But underneath that, the exact same dynamics are happening. In the next video, we'll start discussing current and how to define an operational definition of the current running through an element. See you there.